Next, we're going to discuss the addition rule. This section is sometimes also considered to be about compound events in which two or more simple events occur. So the addition rule says that the probability of the occurrence of two or more simple events is going to look like the probability of A union B is equal to the probability of A plus the probability of B minus the probability of the overlap, the intersection of A and B. Now note that if you have the intersection being a disjoint, right, the overlap of the sets being a null set, then the probability of A intersect B is going to be 0, and so that will basically not be there. It'd just be the probability of A plus the probability of B. And some books will take that and define it as two separate ways of looking at the probability of compound events, the probability of A or B occurring. Now, I think it's really super important for you to realize that this and this are synonymous with one another. The union and the or is what you're looking for. The word or is going to give you context clues in other words. Now we're going to look at the probability of compound events happening in several different ways. One of the ways we're going to look at is a Venn diagram, and that's our first example. And then we're going to look at a two-way table. Now two-way tables are extremely important in terms of some things that we'll do in hypothesis testing at the end of our class. So I want to spend a great deal of time really talking about two-way tables. The contingency tables are two-way tables, but contingency tables are literally given that you have two statistically dependent events. Now, we'll talk about that a little bit later. So the first example that we're going to see is going to be based upon a Venn diagram. The probability that a randomly chosen family will own a color TV is 0.86, a black and white set is 0.35, and both types is 0.29. What is the probability that a randomly chosen family will own either a color or a black and white set? So let's just define as our universe all families out there in the United States. So we'll say that this universe is all families in the United States. So this is where we're drawing our information. Now this example is probably a little bit outdated because we probably should have like plasma TVs and LCDs or something like that nowadays, but we'll just stick with the black and whites and the color sets for sake of argument. So my first one, I'm gonna label this one C for color TV and this one for B for black and white. So that's what I'm referring to. So C is referring to color, and B is referring to black and white. Now, there's no indication that it's not possible for people to have both of those sets, and so that's why we have some overlap here. So the probability of owning a color TV, this probability in and of itself, so I'm going to put this one in bright red, okay, so the probability of being within this set, and this is where we come out a little bit difficult to see, that probability is 0.86. So probability here being 0.86. And then the black and white one, and I'll leave that in black for black and white, the probability of that is 0.35. But then what we have going on is the overlap of these. I'm going to put this in blue. So the overlap of these, both a black and white and a color television set, that is 0.29. So representing these things in terms of some notation, the probability of looking at just a color TV, probability of a C, this looks like 0.86. The probability of a black and white TV, that one looks like 0.35. And then what we have here is the probability of a color and a black and white television set is equal to 0.29. So now that we have all three of those written down and we've visually described them, then our last question is, what's the probability that we have either or? So either or has to count for the fact that when we are looking at the colors or a black and white set, that we double counted those that had the 0.29. So when we were talking about this 0.85 or 86, sorry, this 0.86 already had this 0.29 included in it, right? The overlap. So this set has 0.29 in it. When we were talking about this set over here having the 0.35, we were also talking about those that had the 0.29 in it. And so we included 0.29 in both this set and this set over here, which means that we have to uncount it one time. So the probability rule, the addition rule, looks like the probability of C plus the probability of B. Right? So we say, okay, we're going to have this one plus this one, but then we need to subtract out the probability of C and B so that we get rid of one of these double counts. So now it's only counted through here one time and not twice. So this looks like 0.86 plus 0.35 and then minus 0.29. And so now what we see is the true probability. So let's just calculate that out here. So 0.86 plus 0.35 and then minus, and you see that value there is over 100%. So we know something's fishy's going on, right? And then we count out the 0.29 and that pulls us down to 0.92. And so with that, now we see the probability here is 0.92. Now I have a question for you. Why is it not 100%? Well, if you remember right, when we defined our universe, we said all the families in the United States. Well, because there may be families that don't own TVs, that means that these circles, black and white or color TVs, only represent 92% of the families. In other words, there's 8% of families out here that don't own either a black and white or a color television set. Shocking, I know. Okay, now our next question is going to introduce the idea of a two-way table. Now this two-way table, we're going to be finding the same probabilities that we were before, but from the two-way table, we're going to be building the table from the description. So our first task is to complete a table. So what you're looking at is you're going to look for two sets of characteristics. So you're going to have one set of data and they're going to be classified in terms of two sets of characteristics. So in our example here, we're going to be talking about car dealerships. And one of the car dealerships' characteristics is their type of service. And that's one of the sets of characteristics that we have. Now, in the types of service, we have two different classifications. We have bad service and we have good service. Those are the two types underneath that. But then in addition, we also have number of years of service. So these are the two types of classification, and that's what two-way tables are about. They're taking one group of data and they're classifying them by two sets of characteristics. So these are greater than or equal to 10 years and less than 10 years. Now the thing that the characteristics that you should notice here and the characteristics here is that each of these in and of themselves are mutually exclusive. The types of service, well, you either have good service or you have bad service. You don't have both, you have good or bad. Those are mutually exclusive. Also, in terms of the number of years of service, those are mutually exclusive. You're either greater than or equal to 10 years of service or you've had less than 10 years of service. There's no overlap. So in other words, when we put these into a two-way table, the column values represent one of the types of characteristics, and the row values represent the other types of characteristics. Therefore, our columns are mutually exclusive of one another. Our rows are mutually exclusive of one another. However, a column and a row are going to have dependent events. So someone who has good service, they could have been in service either 10 or more years or less than 10 years. They're going to have both sets of characteristics, and that's what we're talking about when we say dependent events. So dependence here, so dependent events, when I talk about those in terms of a two-way table, I'm talking about the fact that they have both sets of characteristics simultaneously, right? Both sets of characteristics. So you, by the way we've asked the question, can have both good service and have been in service 10 or more years. You can't have good service and bad service, but you can have good service and been in 10 years or more of service. Characteristics, right? So that is what we're going to talk about in terms of dependent events. So let me go ahead and create this table. I'm going to pause my video so you're just going to see all of a sudden, boom, the table's going to be there. All right, so here we go. Now let's read the problem. It says Consumer Service Research Group studied 50 new car dealerships. So you see that down here we have the 50 car dealerships. So everything that's kind of in the borders, those are totals or subtotals or grand totals. So here we have the grand total. It's both the totals of all the good and bads and all the greater than or equal to 10 years or less than 10 years. It's the 50 people that have been surveyed. Of the 50 surveyed, 26 had good service records. So of all those that were good, 26 of them, right? So that's a subtotal. That's the number of good. Now, of these, so of the 26 that had good service, 16 had been in service 10 or more years. So that is a dependence, right? Of the good service ones, there's 10 that have been in service 10 or more, or 16 that have been in service 10 or more years. So we put that in the box of overlap. This represents the number that have this and this. This is, if I called this A and this B, this would be A intersect B's count. So that's what I'm looking at here. Now, therefore, if I'm going to find probabilities of the probability of A and B, it's this out of the total number that's going to be the probability there. Okay, now the next thing it tells me is that of all the dealers, 30 had been in service less than 10 years. So all the ones that have been less than 10 years, there are 30 of them. And that's all it tells us. So from there, we can actually fill in all of the other boxes. So I'm going to change colors. I think I'm going to go for kind of a darkish blue here. So if I want to know what's in this box, well, that's just 50 minus 30, because these have to add up to be 50. So that would be 20. Now these, the same thing, this has to be 50 minus 26, because these two have to add up to be 50. So that would be, let's see, 24. And then we can do the same thing here, right? If this is 20, 16 plus this must be 20. So this must be 20 minus 16. So that would be equal to 4. And then if I know that this is 24, I can do similar here. 24 minus 4 must be equal to 20. And then here, 30 minus 20 must be this box here, 30 minus 20. Or likewise, you could also do this based upon the two black numbers, right? 26 minus 16 has to be equal to the same 10. And it doesn't matter which way you go, it should all add up. I'm going to go ahead and highlight the numbers that are going to be of importance to us so that we can keep track of those. So those are our important ones. So I always go back and I cross-check and make sure that all my row and column totals add up to what they should, and the total adds up. So 16 plus 4